Alright, welcome back everybody. In this video we're going to look at a few examples from the lesson on connecting f prime and f double prime with the graph of f. We'll start here with example 1. Find and classify all of the critical points of g of t equals t times the cube root of t squared minus 4. Give the intervals where the function is increasing and decreasing. So first we want to find all the critical points of this function. And we're going to do that by finding the derivative and seeing where it is 0 and undefined. But first, I'm going to rewrite this to make it a little easier on me when I'm taking the derivative. And it is... Now I can just apply the power rule when I take this derivative. So I've got g prime of t equals t times the derivative of the quantity t squared minus 4 to the 1/3, which is 1/3 times the quantity t squared minus 4 to the negative 2/3 times the derivative of the inside, don't forget the chain rule there, times 2t, and then plus t squared minus 4 to the 1/3 times the derivative of t, which is 1. And cleaning this up a little bit, we have g prime of t equals 2t squared over 3 times the quantity t squared minus 4 to the 2/3 plus t squared minus 4 to the 1/3. And then I'm going to get myself a common denominator here and combine these two terms into a single expression. And so we've got g prime of t is equal to, and I'll use 3 times the quantity t squared minus 4 to the 2/3 as my common denominator. And so I have 2t squared, and then multiplying this term by 3 times the quantity t squared minus 4 to the 2/3 gives us 3 times the quantity 2 squared minus 4 to the first. And then I'm going to combine my like terms and stuff in my numerator. And I end up with 5t squared minus 12 as my numerator. And now I can identify where the derivative is undefined and where it is 0. G prime of t is undefined at t equals plus or minus 2. That was pretty easy. And then g prime of t equals 0 at, and it's going to be plus or minus the square root of 12/5. Plus or minus the square root of 12/5. And since I'm not as comfortable with that number as I am with plus and minus 2, I'm going to decimalize those. So we've got the square root of 12 over 5. So it's plus or minus 1.549. Okay, so we found the critical points. We've decided where they are 0 and undefined. We're going to classify them as maxima and minima. And then we are going to look at where the function is increasing and decreasing. The best tool for this for us is going to be to create a sign chart for g prime. And so I'm going to go ahead and do that. Here comes my sign chart. And I've got negative 1.549, positive 1.549, positive 2, and negative 2. And I want to know where the function is positive, or where the derivative, pardon me, is positive and negative on these intervals. Now I can go ahead and substitute a value into each of these intervals to figure out the sign, or if I have access to my calculator, I can do it all in one fell swoop by graphing this derivative. Which is what I'm going to do here to save myself a little bit of time. I have the right number of parentheses there. And so we'll look at the graph of this derivative, which shows that the derivative is negative between negative 1.549 and 1.549, and it's positive everywhere else. Okay, so let's take a look at what I have here. I have a maximum where the derivative sign changes from positive to negative, and so that's going to happen at negative 1.549, and whatever the y-coordinate of that is, we'll find that in a second. I have a minimum where the derivative changes sign from negative to positive, so that's at 1.549, and whatever the y-coordinate is of that point. And then as far as my intervals of increasing and decreasing, it is increasing everywhere where it's positive, and it continues to, so we've got from negative infinity to negative 2, and from negative 2 to negative 1.549. And from 1.549 to 2, and from 2 to infinity. And it's decreasing from negative 1.549 to 1.549. Okay, now I need my y-coordinates for my original function. I'm going to go ahead and put the original function in here. Set up my table to ask, and I want the square root of 12 over 5. We get negative 1.812 for the y-coordinate there, and for negative, square root of 12 over 5, we get positive 1.812 there. Alright, and then just to verify, and since I have it in here, if I look at a graph of this, there we see what the graph looks like. And I guess really technically, these points right here where the derivative was undefined, I guess the function really is increasing there. It just basically has a vertical tangent for a moment. So I could smooth these intervals of increasing out and just make it from, make it from negative infinity to negative 1.549. And from 1.549 to infinity. Sorry, I ran out of space there. Alright, let's go on to example 2, which is about finding concavity. I'll try and move through this one fairly briskly. Here we're going to identify the intervals where the function is concave up and concave down, and identify any points of inflection. We're going to use a sign chart again to help us out in this process. But in order to identify where it's concave up and concave down and where points of inflection occur, we're looking at the second derivative. We're going to make a sign chart for the second derivative. So I first find the first derivative, which is 15x to the fourth minus 15x squared. And then I find the second derivative, which is 60x to the third minus 30x. And so to find where the points of inflection occur, I'm looking for where this second derivative is either 0 or undefined. And so we can find those values. We'll factor this out. 30x times 2x squared minus 1. And so h double prime equals 0 at x equals 0. And then we need x squared to be equal to 1/2. So it's 1 over the square root of, plus or minus 1 over the square root of 2. So this is plus or minus root 2 over 2, which, if you don't know that off the top of your head, that's approximately 0.707. All right, and so now we're going to look at a sign chart of the second derivative. Notice how I always label my sign charts with what they represent. That's very important. All right, so we've got negative root 2 over 2, and 0, and root 2 over 2. And again, I can analyze and find the value of the sign here one interval at a time, or if I have access to a calculator, I can use a graph of this second derivative to help me decide what's going on. So 60x to the third minus 30x. And if we look at the graph of this second derivative, it's a little hard to see, but if you stretch this out a little bit, you can see that the derivative is negative to the left of negative root 2 over 2 because the second derivative, because the graph is negative there. And then it's positive from negative root 2 over 2 to 0, and then it's negative, and then it's positive. And you can see all of that by just looking at the graph. This is a graph of the second derivative, so wherever it's below the axis, it's going to be negative on our sign chart. Wherever it's above, it's going to be positive. All right, so let's identify it is concave up from negative root 2 over 2 to 0, and from root 2 over 2 to infinity. It is concave down from negative infinity to negative root 2 over 2, and from 0 to root 2 over 2. And we have points of inflection everywhere where it changes concavity. So we have points of inflection at negative root 2 over 2, whatever the y-coordinate is, 0, whatever the y-coordinate is, and root 2 over 2, whatever the y-coordinate is. And so we're going to put these back into the original function to find the y-coordinate. 0 is easy enough, and for root 2 over 2, I'm going to go back and look at the original function. And go to my table and put in root 2 over 2 and negative root 2 over 2. And I get those y-coordinates. At root 2 over 2, it's 1.763. And at negative root 2 over 2, it's 4.237. So there are points of inflection and our intervals of concave up and concave down. All right, that's just about all the time we have for this video. See you guys next time when we look at the other examples from this lesson. Have a great rest of your day.